This is Algebra 3. We're going to talk about Unit 7, which is the normal distribution, okay? We're going forward into a little bit more of statistics. We're going to just talk about some college level statistics. We will investigate the normal distribution, its shape, and how to calculate some probabilities, something we have discussed earlier in the year. Section 7.1, the normal distribution, can be applied to many data sets in the real world. And we want to talk about z-scores and also area underneath a curve, specifically any bell-shaped data set. There's a little strip of area underneath the curve. Let's motivate with an example. Draw a bell curve for each data set on the same number line. And you can see that below I've made a number line that goes from 0 to 25. The reason why I've done that is because with all three data sets put together, the minimum value is 1 and the maximum is 21. So if I go from 0 to 25, I'm going to get everything in there. Let's use a graphing calculator and look up one variable statistics for each. We're going to get the mean and we're going to get the sample standard deviation. And recall that's going to be S subscript X. Okay, so for the first data set, 11477, we should get a mean of 4 and a sample standard deviation of 3. Comes out really nicely. The next one is going to be a mean of 10 and a sample standard deviation of 2. And if you haven't already, try the third set on your own. But you should get a mean of 20 and a sample standard deviation of 1. Now, I am going to graph 3 different bell curves that demonstrate what each data set looks like. So the first one here, A, has a mean of 4, and that's going to be right where the center of the bell is. And the standard deviation is 3. Notice that that's larger than the other two. So this bell is going to be wider, apex at 4, and then come back down. I just want to give you an idea of how different data sets look when it's a bell curve. You can see in the second one that 10 is going to be the center of it. But the standard deviation is less than part A. So what I have to do is try and draw my bell curve, but it's going to be a little bit skinnier. Apex at 10. And a little bit taller. So we've got that full amount of data underneath that purple curve. Finally, the third data set has a center at 20, but the standard deviation is 1. So this has to make the data set even more compressed together. So let's make this a really skinny bell curve. It's going to go pretty high, apex at 20, and come back down. But what we're going to say is the smaller the standard deviation, the less spread out the data set. Let's think of all of these as normal bell curves. If a data set has a bell shape, and the example that I'll throw out is height of the class. properties of a normal distribution, and let's see if it matches up with characteristics about, say, the height in inches of everybody in the class. A normal curve is bell-shaped. So if the class average is 5 feet 5 inches tall, then there should be half of the class is going to be shorter than 5 foot 5 inches, and the other half of the class is going to be taller than 5 feet 5 inches. The highest point, therefore, is the mean. And that's going to be X bar for a sample. The mean, median, and mode are all the same. Strangely, what that means is, well, the mode, there's probably going to be only one value for each of them. And that'll probably be, so that means there's basically no mode, and that the center of the distribution would have to be where the mean is. And then the median, 50% of the data is below and 50% of the data is above. The curve is symmetric, you can split it in half. And that's why I said half the class would be less than 5 foot 5, half the class greater than. The total area under the curve adds up to 1. So what that means is that's 100% of the data is under the curve. Now, finally, 68% of the data lies within one standard deviation of the mean. 95% of the data lies within 2 standard deviations, and 99.7 lies within 3 standard deviations. Think about an example with height of students in the class. If the mean or average would be 5 feet 5 inches, and let's say the standard deviation is 1 inch, so between 5 foot 3 to 5 foot 7 would be 95% of the students. Notice that I took 5 feet 5 inches and I subtracted 1 inch and 1 inch and then added 1 inch and 1 inch. And you would get 95%. It'll make more sense in the next example. So we can turn this thing into a rule and call it the 68, 95, 99.7 rule. In a normal distribution, meaning a bell-shaped data set, 68, 95, and 99.7% of the data lie within 1, 2, and 3 standard deviations of the mean, respectively. Here's what that's going to look like. Right in the middle is the mean. Okay, that's a population mean because we wrote mu instead of x bar. If I go to the left by 1 standard deviation, I'm subtracting. So mu minus the standard deviation. And that letter right there is the population standard deviation, okay? So this will work with population or sample. Let's make this a different color. I can also add 1 standard deviation up. Think about that, what that means. Let's go back up to the original example here. Let's say we're talking about the first data set. If the mean is 4 and the standard deviation is 3, so that means if I add 3 to each side, if I add 3 and I subtract 3, so right in between there would be 68% of the values. So this is right here is going to be 4 plus 3, which is 7, and that's where I am on the number line. And this is going to be 4 minus 3, which is 1, and that's exactly where I am on the number line, okay? So adding a standard deviation and subtracting 1. If I do that again, then I'm going to get mu minus 2 sigma and mu plus 2 sigma. In between there should be 95% of the data. And then I'm going to do that one more time, and here will be mu minus 3 sigma and mu plus 3 sigma. Let's put it into a bell curve. Okay? So, one more time. From mu plus 3 sigma to mu minus 3 sigma, that's 95% of the data, okay? What that would mean is in the tail here and here would be 5% left over. So if I take 5% and I divide it by 2, that would be 2.5% of the data. Let's think about the example with height in the class. If the mean height was, say, 5 feet 7 inches, let's make it 5 because that's what we were talking about before. So 5 feet 5 inches, and the standard deviation was 1 inch, then over here it would be 5 feet 2 inches, and up would be 5 feet 8 inches. So 95% of the students would have a height of 5'2" to 5'8". 2.5% of the students would be greater than that, and 2.5% would be less than 5 feet 2 inches. Whoa, a lot of stuff. But this allows us to analyze percentages on any data set that has a bell shape. There it is. Suppose that on the SAT, 500 students scored an average of 975 with a standard deviation of 125. So let's assume this is a population, and we'll write mean 975, standard deviation 125. What scores lie within the data for 68% of it? Well, for this one, I'm going to add 1 standard deviation to each of them. So if I take 975 and I add 125, that should get me 1100. If I take 975 and I subtract 125, that should get me 850. So 68% of the data values lie between 850 and 1100. 68% of all SAT scores would be between 850 and 1100. Okay? Notice that I used X as the score, and I used less than or equal to signs to make a compound inequality. Graphically, it would look like this. 68% of the data. The mean would be 975. This score in red would be 1100, and below would be 850. I encourage you at this point to pause the video, try part B and part C, and see if you can figure out 95% of the data and 99.7% of the data, the scores, and write them as compound inequalities. All right, for part B, I'm going to take the mean, and I'm going to add 2 standard deviations. So 2 times 125 should get me 1225. And then for mu minus 2 sigma, I'm going to take 975 minus 2 times 125. That will give me 725. So our values should be between 725 and 1225. For 99.7, I'm going to change this to a 3. So my scores, 99.7 of all SAT scores should be between 600 and 1350. Now, last one, part D. How many students, so we're not talking about a score or a percentage, how many students scored higher than 1350? Well, if there are 500 students that took it, and 1350 is 3 standard deviations above the mean, let's go back up to the picture and figure out what percentage goes right here, because that's above 1350. So if I know that, say, 99.7% is between these values, 99.7, and subtract from 100, is 0.3%. If I divide that by 2, I get 0.15. So this is going to be 0.15%. Okay, now I'm going to take 0.15% and multiply it by the number of students who took the SAT. But I have to convert that 0.15 into a decimal. So that's going to be 0.0015 times 500. And this is going to be 0.75 students. So not even one student would score above a 1350. There you have it. I encourage you to comment on this video in order to earn credit, and then have a nice day.